All right, well, it's about time for this. Let's formally define what a linear functional is, this being functional analysis and all. What we'll do in this section is classify the bounded linear functionals on a Hilbert space. In fact, we'll see that the bounded linear functionals themselves form a Hilbert space. So we're going to abbreviate this section a little bit given by prom. So I've put together a supplement that'll deal with that. So we'll deal with the proof elsewhere. But to formally define a bounded linear functional, for X, a normed linear space with scalar field F, a bounded linear functional is a bounded linear operator, where the output is the normed linear space, the scalar field. So we'd have to have something like absolute value on the scalar field, and we'd likely take the scalar field to be the real or the complex numbers. So what functionals do is they take elements of normed linear spaces in, which we usually interpret as functions. Most of the applications of this stuff involve normed linear spaces where the vectors are themselves functions. And it's common to think of a functional as mapping functions to numbers. So that's the types of things they take in and that they give out. Anyhow, we've encoded all this in the lingo of bounded linear operators between normed linear spaces. We'll denote the collection of bounded linear operators, or excuse me, bounded linear functionals from X to scalar field F as X star will be the notation. In the event that we're dealing with a Hilbert space, we'll see that H star itself is a Hilbert space, and it's called the dual space of the given Hilbert space. So we can look at these X stars regardless of the structure of X, but it's the Hilbert space applications that we're interested in. The next result is what would be called a representation theorem. It gives a classification of bounded linear functionals in terms of inner products. If we were to deal with this in the setting of the classical Banach spaces, the LP spaces, this result would be definitely called the Reese representation theorem. I kind of prone to call it the Reese representation theorem, even in this more specific setting of Hilbert spaces. There are certainly LP spaces that are not Hilbert spaces. For any Z, a vector in a Hilbert space H, the functional psi sub z defined by psi sub z of X is the inner product of X with Z. Claim is this is in the dual space H star, the bounded linear functionals from the Hilbert space to the scalar field. And conversely, given any F in H star, there's a unique vector Z in H such that F equals psi sub z. So what this means is certainly inner products are examples of functionals. Inner products are, well, they're linear in the Promislow reference. They're linear in the first position. So we do get linearity out of these. The boundedness, I guess, is some details to check. And what Theorem 4.22 is saying is not only can we use inner products to produce functionals, and certainly the inner product gives a scalar out. So we're taking a vector in and getting a scalar out as we should. But every bounded linear functional on Hilbert space H is of this sort. So not only are inner products useful as examples of bounded linear functionals, that's all the bounded linear functionals there are on a Hilbert space, those which are related to inner products like this. I've got a little problem myself with Promislow's proof of Theorem 4.22, so I'll defer to a supplement to deal with that. We'll just take this as given, though we do need some results from the proof that we'll mention here shortly. So Theorem 4.22, as I said, tells us that every element of the Hilbert space corresponds to a bounded linear functional Every z corresponds to a psi sub z. Here's the form of it expressed in terms of an inner product. And conversely, every bounded linear functional in H star corresponds to a psi sub z, corresponds to a mapping of this sort. And as I said, this is often called the Reese representation theorem. It tells you linear functionals are effectively inner products and vice versa. So we'll define a mapping J sub H as the mapping from H to H star that sends vector z to the associated psi sub z bounded linear functional. Theorem 4.22 tells us we have this correspondence, this one-to-one correspondence between vectors and psi sub z's. So it tells us this J sub H mapping is bijective, one-to-one and onto. And as we would see going through the proof of Theorem 4.22, we will have a corrected proof of it in the supplements, that the norm of psi sub z equals a norm of z. In other words, J sub H is an isometry. This input z that would go into J sub H has a certain norm, and its image has the same norm. Its image, the image of z under J sub H being the psi sub z mapping. But it's not linear. It turns out it's conjugate linear. So if we were to look at J sub H of Iy, so we're going to take Iy in, this should give us out a bounded linear functional, an element of H star, the dual space. So the X is acting as an argument, kind of an f of X style. But J sub H will map Iy to psi sub Iy, and that's how J sub H was defined. So we get out psi sub Iy, dummy variable is X. What does psi sub Iy do to X? Takes an inner product. Takes the X goes on the left, and the subscripted stuff was on the right part of the inner product. So what we would get from this would be the inner product of X with Iy, but in Promeslow's definitions, we have conjugate linearity in the second entry. So we'll bring that out front as a negative I. So take the scalar I out as a negative I, conjugate linearity in the second position. Now we've got an inner product of X with Y. Well, that is psi sub Y, the way the psi sub Y functionals were defined. Psi sub Y as a mapping is J sub H of Y. J sub H would take Y and associate it with psi sub Y. So there it is expressed in terms of the J sub H's. And what's ultimately happened is this I scalar we had inside the J sub H mapping has come out as a conjugate. It's come out as a negative I, not as an I itself. So we're not getting linearity in these J sub H's. We're getting conjugate linearity. Corollary to the theorem. We'll give an argument for this within the notes, so we're approaching this section a little bit different. For any Hilbert space H, the dual space H star is in fact a Hilbert space with the same dimension as H itself. So take G and F to be from the dual space to be from H star. The theorem 4.22, what I want to call the Reese representation theorem, tells us that F equals psi sub X and G equals psi sub Y for some vectors X and Y in the Hilbert space. So we will define the inner product of F with G to be the inner product of Y with X. And not an error, the order's changed. So the order different. The F was associated with psi sub X. The F is first here, and the X is second on the right-hand side. But that's the way we're defining the inner product. So this makes sense because this is stuff that's happening inside the given Hilbert space H. This is a definition that's going to give us an inner product on the dual space H star. Then H is an inner product on H star, and the norm on H star is the one induced by this inner product. So there's something, this is the idea of the proof. There's something that could use the details checked. But with that taken as true, continuity of the inner product, we saw, I guess, in Theorem 4.9, says if we had a Cauchy sequence in H star, that's going to correspond to a Cauchy sequence in H. Taking limits of partial sums is what we probably deal with in that case to talk, partial sums. The Cauchy, the A sub n, A sub m idea of Cauchiness. But Cauchy sequences will correspond to Cauchy sequences because we get a pretty close correspondence in terms of norms. We get the same norm, in fact, correspondingly is given here. We'll get limits to behave in a corresponding way. If we take Z1 and Z2 from the Hilbert space, where Z1 and Z2 have an inner product of 0, that is, they're orthogonal. We're making a claim about, making a claim about dimension here, aren't we? Then in the dual space, if we would look at J sub H of Z1 and J sub H of Z2, the J sub H's simply produce the psi's. So that gives us a psi of Z1, psi of Z2. Z1 appears in the first position, Z2 in the second. When we convert that into an inner product, as we've defined up here in H, that'll give us the inner product of Z2 with Z1, as observed above. Seems like we've swapped some things around, but that was a definition. That's how we define the inner product on H star. And the inner product of Z2 with Z1 is the complex conjugate of the inner product of Z1 and Z2, but we said that was 0, so we get 0 conjugate out, we get 0 out. So if we have an orthonormal basis for H, then we've got orthogonality preserved, we've got norms preserved. So this X sub n will produce this orthonormal basis of X sub n, a basis of H, can be used with a mapping J sub H to produce an orthonormal basis of the dual space of H star. I think this preserves, since J sub H is an isometry, that's possibly contained in the proof of Theorem 4.22 as well. So bases correspond, orthonormal bases correspond. The dimension of H and the dimension of H star will be the same. Under this notation, the orthonormal basis of H produces this orthonormal basis called a dual basis of the dual space. Now, we know every infinite dimensional separable Hilbert space is isomorphic to L2. Promeslow's result, what I call the fundamental theorem of infinite dimensional vector spaces, with a lather of detail. The separability certainly plays a role. Then the dual space of any infinite dimensional separable Hilbert space is that space itself, because all these spaces are isomorphic. And we get H equals H star. H is said to be self-dual in that event. This could have been done, this idea of functionals could have been dealt with, in fact, in the Banach space setting. It often is in the setting of the LP spaces. Remember, in the LP spaces, the only one that's a Hilbert space is when P equals 2. But we could have dealt with the LP spaces and bounded linear functionals and have a certain type of representations of those related to integrals, it turns out. And the only one of the LP spaces, which is self-dual, it turns out, is when P equals 2. So not surprising, given what we know about L2 and the fundamental theorem of infinite dimensional vector spaces. So that takes care of getting the idea of a linear functional formally defined, though we did skip some of the details, and we'll leave that for the supplement to go through and give an accurate proof of the Reese representation theorem in this setting. We'll see you later. Have a nice day.